Today's topic is momentum. So which one is harder to stop? A 40 kilogram person going 1 meter per second or a 40 kilogram person going 10 meters per second? And so as we're going through the topic of momentum, we'll be able to answer this question. So momentum refers to the quantity of motion that an object has. It can be defined as mass in motion. It is a vector quantity. That means it has a direction, but it is very different than inertia. The amount of momentum that an object has is dependent upon two variables: how much mass is moving and how fast it's moving. And so momentum is represented by lowercase p, and it's in kilograms per meter second because p equals mv, which is mass is in kilograms, and v is in meters per second. And so when we combine those, that gives you your unit for momentum, which is kilograms per meters per second. So if an object is at rest, it has no momentum. So here's where it is different from inertia. When we talked about inertia, we said the more mass, the more inertia it has. Less mass, less inertia. But here, in order to have momentum, you have to have a velocity. Because if you don't have velocity, you will have no momentum. So which one is harder to stop? 30 kilogram person going 1 meter per second or a 40 kilogram person going 0.5 meters per second. So let's do the calculation there. So the top. Let's put our variables down first. P is question mark. We don't know that yet. M is 30, V is 1. So P equals mv. We substitute mass for 30 kilograms times 1 meters per second. That gives us 30 kilograms per meters per second. That is our momentum for A. Same thing with B, but now our mass is 40 and our velocity is 0.5. And that gives us 20 kilograms times meters per second. And so we find out that the top, A, it's harder to stop because it has a greater momentum. So don't let the fact that it has something has more mass or make it look bigger mistake it for having momentum. It doesn't necessarily mean it's going to have more momentum. It has to do with velocity as well. So which object has more momentum? The car on the top has 820 kilograms, but it's going 45 meters per second or 101 miles per hour, or a 36,287 kilogram 18-wheeler going 1 meter per second or 2 miles an hour. So the top, our mass is 820 times velocity, which is 45, gives us a momentum of 36,900 kilograms per meters per second, and that is our momentum. As opposed to the bottom, while it does have a great mass, it doesn't have enough velocity. And so our velocity there is 1, and our momentum is 36,287. So it has slightly less momentum just because the velocity is not great enough. And so A has more momentum. So what is the mass of object A? And what is the velocity of object B? So if you look at object A, that gives me momentum, because the unit for momentum is kilogram times meters per second. And it gives me velocity, 30 meters per second. So that's great. I can figure out mass. B gives me mass and it gives me momentum. I have to find velocity. Okay, so P equals mv. We plug in P as 10,500 equals m times 30. And to get m by itself, I divide both sides by 30. And I get 350 kilograms. That's how much object A is. Now in object B, we're looking for velocity. So our momentum was 17,550 equals our mass, which is 1,300 times v. To get v by itself, I have to divide both sides by 1,300, and I get velocity is 13.5 meters per second. So the direction of the momentum vector is in the same direction as the velocity vector. And so sometimes we'll say we have positive momentum or negative momentum depending on the direction. So to fully describe the momentum of a 5 kilogram bowling ball moving west at 2 meters per second, you must include information about both the magnitude and the direction of the bowling ball. So what is the complete answer? Making west, left, negative. So let's look at that. So m is 5. Our velocity is negative 2 because we're moving west towards the left. So 5 times negative 2 gives us negative 10. That means it's moving 10 kilograms times meters per second to the west or to the left. So you can also plug in numbers and calculate, but what about conceptual word problems? If we plug in ones for mass and velocity, we can tell what happens to the momentum. So momentum is directly related to mass and velocity. So let's say a car possesses 20,000 units of momentum. What would be the car's new momentum if velocity is doubled? If it's doubled, we just double 20,000. So 20,000 times 2 would be 40,000. If velocity is tripled, we just merely multiply it by 3 and r. So just to see how I'm getting these, P equals mv. And we plug in 1 for mass, but our velocity tripled. So it's just 20,000 times 3. If mass was doubled, so m changed to 2 by adding more passengers and a greater load, we keep that the same. We just multiply momentum by 2. So 20,000 times 2. Both if velocity was doubled and mass was doubled, so that's times 4. So 20,000 times 4 is just be 80,000. So recall Newton's third law. We're not going to combine Newton's third law with a relationship between force and momentum. And so this is called the law of conservation of momentum. The total momentum in a system of interacting objects cannot change as long as all forces act only between the objects in the system. So let's talk about that. So when two objects exert forces on each other in an action-reaction pair, their motions are affected as a pair. So remember, when we were dealing with forces, we're dealing with two things, not just one. And so the law says that the total momentum of the system remains constant. So, for example, on the left we have m and v. The momentum on the left or on the opposite side has to equal the other side, mv. So basically we can say the same thing. We can say m, right? M still stays the same here. Remember, this represents a change, so final minus initial equals m, and then again final minus initial of our second velocity. So let's see how we can work with this. So let's look at that concept. So if you stand on a skateboard and throw a bowling ball, you apply a force to the ball. And so the momentum here, P equals mv, our mass is 5 and our velocity is 4 meters per second. So our momentum here is plus 20. So if the ball gains plus 20, you also must gain negative in the left side, on the opposite side. So here your momentum is 40 times negative 0.5 because you moved back. You have these action-reaction forces, and that equals negative 20. And so we see that they're both equal in momentum, but in opposite directions. So the third law says the ball exerts an equal and opposite force back on you, just like we saw. Therefore, your momentum also changes. And since forces are exactly equal and opposite, the changes in momentum have to also be equal and opposite.